Okay, thank you very much. Thank you very much for the invitation to speak. This is the fourth of a series of lectures, and hopefully the other three were comprehensible, and we can sail through this one as well. So we want to discuss ideas today about constructing what we would be calling a p-adic gamma function. A useful research program is to see if there are analogs, search for analogs of classical functions. Last time we discussed the exponential and logarithm functions, and today we want to discuss the p-adic version of the gamma function. Now we'll consider first continuous functions from ZP to QP and begin with the p-adic analog of the classical problem of interpolating factorials. You'll remember that Euler first observed that the integral from 0 to infinity e to the minus x to the n dx is n factorial, and is that the left-hand side makes sense if you replace n with the complex variable s. And this observation led Euler to construct his gamma function. And this gamma function is defined as some integral from 0 to infinity e to the minus x to the s dx. Now I'm noticing that there's this window that keeps showing up. So I'm just going to stop share and start sharing again, if you don't mind. Let me just do that. Okay, so that hopefully that window will disappear. Yeah. Okay, so how to look for the p-adic gamma function? The p-adic analog of this problem has no solution, because if you look at n factorial tends to 0 in the p-adic metric, because as you take more and more n's, there are going to be higher and higher powers of p. So it makes sense maybe to consider not the product of the first n natural numbers, but maybe we should consider only those natural numbers product which is less than n with j coprime to p. Otherwise, we're going to get into a mess. Maybe this should be the p-adic analog of the factorial function. And this leads to a question of p-adic interpolation. Just as the gamma function interpolates the sequence of factorials, well, we can ask a general question. Suppose I'm given a sequence of numbers a sub k. When is there a continuous function on the p-adic integers such that f of k is a sub k? And since z sub p, we mentioned last time, is a compact vector topological space, such a function must be uniformly continuous and bounded. Therefore, a necessary condition is that for each m, there must exist an integer n of m, such that whenever k and k prime are closed p-adically, ak and ak prime must be closed p-adically as well. So you see, this point is you can't ask for any arbitrary sequence to have a p-adic interpolation. The sequence has to have some sort of congruence properties. Now, we already met something like this. You remember in the early lectures, we talked about Bernoulli numbers, b sub k over k, and the Kummer congruences. So the Kummer congruences are really a statement of this shape. And so that's already signals that there's something profound and deep going on. We're just only now scratching the surface with the concept of a p-adic vector space. So whenever k and k prime are closed p-adically, then ak and ak prime should be closed p-adically as well. Conversely, if 5.1 condition is satisfied, then the supremum of the a sub n's must be bounded, and we can define a continuous function on ZP as follows. So p-adic interpolation. So the theorem is, supposing I'm given a sequence of numbers f of k, which is p-adically bounded and satisfies the following condition. For each natural number m, there's a natural number capital N, so that whenever k and k prime are closed, f of k and f of k prime are also closed. So this is like saying for every epsilon, there exists a delta, right? The continuity of a real valued function is, the formal definition is that for any epsilon positive, there exists a delta such that whenever x and x prime are close together, f of x and f of x prime are closed. That's uniform continuity in the context of real analysis. So in the context of p-adic analysis, something exactly identical. In such a situation, we have a continuous function which extends these values. So this is basically what the theorem is. This allows us to extend f to z sub p as follows. Just simply take a limit of ordinary numbers ni such that ni tends to x, then f of x, this will be defined as f of the limit of f of ni. And this actually works because of the condition 5.1, or the condition here that I outlined here as the essential condition. So the limit exists by virtue of that condition, and if ni prime is any other sequence tending to x, it's easy to see that the two limits are actually the same because, again, of the condition 5.1. So the function is actually well defined. So now I think we understand what p-adic interpolation is all about. You give me any sequence of numbers that satisfy this condition, k congruent to k prime mod p to the n implies f of k congruent to f of k prime mod p to the m. That kind of condition, if it satisfies that, then you can actually interpolate the thing. So this interpolation reduces to checking whether this 5.1, which I keep calling 5.1, whether this is satisfied or not, this condition. So that's the key condition that we have to kind of check. So before we move to applying this theorem to the context of the Kummer congruences and trying to derive the p-adic zeta function, I thought it might be helpful for the students in the room to understand p-adic interpolation of the gamma function. It's a little easier. And so let's try and do that, because the knowledge of interpolating the gamma function is very minimal, and it only requires knowledge of Wilson's theorem, which is a theorem in elementary number theory. So we have this interpolation theorem. As an application, let's first of all start off even with the more baby example. Try to interpolate n to the k. Supposing my sequence is f of k equals n to the k. Does that extend to a p-adic continuous function? So if n is congruent to 1 mod p, then this actual condition can be easily verified. If n is congruent to 1, we can write n as 1 plus a multiple of p. And so what is the condition we have to check? We have to check whenever s and s prime are closed, we want to check is f of s and f of s prime close. So what is f of s? F of s is n to the s. What is f of s prime? It's n to the s prime. So we take the difference and we look at n to the s times 1 minus n to the s prime minus s. And then because s prime minus s is s double prime p to the n, and n is equal to 1 plus mp, we can now use our binomial expansion and see that the ones disappear, and then you're going to get higher and higher powers of p. So indeed, you are able to see that n to the s and n to the s prime are getting closer and closer p-adically, and therefore, indeed, we can interpolate n to the k, the sequence of values n to the k, whenever n is congruent to 1 mod p, we can interpolate that sequence and find a continuous function such that at those values, at k, you have this value n to the k. So this is a baby example to get us started, to see that what a remarkable world will be revealed if we take a p-adic perspective. So in the case of the p-adic gamma function, let's now consider the sequence. I told you we just simply cannot take the factorials because the factorials are going to 0 p-adically. So we remove those numbers which are divisible by p, and only take the product of the numbers j less than k, where j is co-prime to p, and that's our sequence. And see, let's just check if that condition 5.1 is satisfied or not. And the verification turns out essentially to be Wilson's theorem. We must compare the p-adic distance between a sub k plus p to the s and a sub k. So we just write down the definition of a sub k plus p to the s. It's the product of all the numbers from 1 to k plus p to the s, which are co-prime to p. And then that can be factored as the product of the numbers up to PDS, and then PDS to K plus PDS. The first factor is just the product of a complete set of coprime residue classes mod PDS. Now remember, in a group, in an abelian group, if you take the product of all the elements of the group, you can pair up the element G with G inverse. And since it's an abelian group, the product will turn out to be 1. The only problem is, what happens if G and G inverse are the same? You're not going to be able to pair that up. And so in any abelian group, the product of all the elements of the group is the product equal to the product of all the elements G, such that G squared equals 1. So in this case, what are the elements, residue classes X, that coincide with their own inverse? That means X squared is going to be 1 mod PDS. And you will recall in a previous lecture, I mentioned that the only solution when P is an odd prime, the only solutions are plus or minus 1 from Hensel's lemma that we discussed last time. So therefore, A sub K plus P to the S is just the product of plus 1 times minus 1, which is minus 1. And then you have the elements product J going from P to the S to K plus P to the S. And that's our definition of that is a simple modulo P, P to the S rather, modulo P to the S, that's the same as A sub K. So if we make a slight change in sign, in sign adjustment, we might be able to do it. So we're off by this minus sign. So that means that perhaps this naive way of trying to talk about factorials as the product of all the numbers just less than K, which are coprime to P, is not completely right. You may have to fudge it with a sign function. So let's look at that. So this is what's called the Morita p-adic gamma function. Morita defined in 1975 the p-adic gamma function as follows. The value at 0 is 1, and the value at n is minus 1 to the n times product of the j's, j less than n, j coprime to p. So instead, before we didn't have this minus 1 to the n, but now we see why we need to put that in because of that condition 5.1 we need to check. And now if we want to check that condition, we find that gamma p of k plus p to the s is congruent to gamma p of k mod p to the s. And sure enough, it satisfies that condition. So the existence of a continuous function is now established. So this is the way we extend the p-adic, this is the p-adic analog of the gamma function. Now, this is only discussed now so far for p odd. So we need to take some caution, have some discussion about p equals 2. So before I do that, let me just say the classical theorem of Weierstrass that a continuous function on a closed interval can be uniformly approximated by polynomials. This is the version of that. The p-adic analog of this is Mahler's theorem. And Mahler's theorem says that if you give me any continuous function on ZP, there are numbers C sub k such that f of x can be expanded as this kind of binomial series. It's like a power series expansion. And the partial sums of this series are the desired polynomials. So it's not quite as clean and neat as we have it in the case of the Taylor series expansion, but it's pretty close. So as a prelude to Mahler's theorem, let me just recall some basic facts from elementary number theory. X plus y to the power p is congruent to x plus y mod p because all the binomial coefficients in the middle are divisible by p. So this is just Fermat's little theorem again. We can look at the 1 plus x to the n as a power series in x.
Isn't it x to the p plus y to the p?
Pardon me?
X to the p plus y to the p instead.
Yeah, x to the p plus y to the p, but x to the p is x. That's Fermat's little theorem.
Okay.
Yeah, we can look at 1 plus x to the power n as a power series in x, and the coefficient of x to the k is the binomial coefficient n choose k. And so now we can use this elementary observation to come up with what are called Lucas congruences, or Lucas, Lucas congruences for binomial coefficient, Lucas came up with an ingenious observation that the question of what is n choose k modulo p, well, he says, well, you write n in base p and you write k in base p, and lo and behold, n choose k turns out to be A0 choose B0, A1 choose B1, A2 choose B2, dot, dot, dot. Of course, it stops after a while, but that's the nice way of discussing this congruences. And with this particular observation, many congruences with the binomial coefficients get simplified. So in the proof is very simple. You just write 1 plus x to the power n. You write the n as in the p-adic expansion, and you write 1 plus x to the A0, 1 plus x to the PA1, and so on and so forth, and then you apply induction. So the p divisibility of the binomial coefficients is now easily understood. Now, if I want to say is p choose k was clearly divisible by p, but is p to the n choose k divisible by p? And the answer is yes, because of the Lucas theorem that I just talked about. What is the p-adic expansion of p to the n? Well, p to the n, it's already there. And then what is the p-adic expansion of k? Well, whatever it is, it doesn't matter, because once you've taken the p-adic expansion of p to the n, the first coefficient is just simply 1, and everything else is followed by zeros. Therefore, you end up immediately getting this congruence for all the k's between 1 and p to the n minus 1. That's a beautiful way of getting this. This is, I think, not generally taught in elementary school, and it might be a nice exercise to give to your class on elementary number theory. So let's also recall there's something else we need to do before we discuss Mahler's theorem, and that is what's called the binomial inversion formula. I'm not going to prove it. I'm just going to state it. So if I have a sequence of numbers b sub n, given by n choose k, a sub k, then I can invert. I can solve for a sub k. And how do you do that? Well, you do this by a sub n is equal to n choose k minus 1 to the n minus k b sub k. This is actually a special case of what might be called the theory of the Mobius inversion on a partially ordered set. So you can have a fancy formulation, or you can have even a simpler formulation. You can just simply use generating functions to prove this identity, or you can just crank it out by brute force. And how would you crank it out by brute force? Well, you would use what's called this in orthogonality relation. So if you fix a positive integer m and set a sub k to be minus 1 to the k, then the above binomial inversion gives an orthogonality relation, this relation, that summation minus 1 to the k, n choose k, k choose m, is minus 1 to the m if n equals m and 0 otherwise. So you can kind of prove that also just with bare hands. And then once you have this orthogonality relation, the inversion formula is very easy to check. So I'm going to leave that as an exercise and not waste too much time here, but that idea will be needed in the course of the proof of Mahler's theorem. So an application of the binomial inversion formula is that if I have a continuous function, a p-adic continuous function, and I define sequence a sub n of f, which is just simply n choose k minus 1 to the n minus k f of k, I make this definition, then the binomial inversion formula tells me that f of n is equal to n choose k a sub k of f. So this is giving us a prelude as to how we should go about trying to prove Mahler's theorem. This is very simple, very elementary combinatorial ideas. So this suggests how we can solve the interpolation problem. You give me a sequence of numbers, f of 0, f of 1, f of 2, dot, dot, dot. Define a sub n of f by that 5.5, this formula here. And then set f of x as simply to be summation x choose k, a sub k of f. If you just define it like that, then it will satisfy those properties. But the question is this now a p-adic continuous function or not? Well, that we'll have to check later on. Now, if we can show that this is a p-adically convergent series, we're done. Observe that x choose n, when I keep writing x choose n, it's a binomial coefficient, but also if it's thought of as a binomial coefficient, you may be stuck with x being an integer, but it doesn't have to be, because the binomial coefficient can be written as x times x minus 1 x minus n plus 1 over n factorial, and the numerator makes sense for any real number. So you can define x choose n for any real number in this fashion. So it's a continuous function of a p-adic variable, takes integer values whenever x is an integer. So we can think of the binomial coefficient in this larger sense of the word, and then work with that. Also notice, because it's an integer, we find at integers, x choose n has a p-adic norm at most 1. And because the integers are dense in ZP, we see by continuity that the norm is always less than or equal to 1 for all x in ZP. Okay. One more idea that I need before we start the proof proper of Mahler's theorem is this concept of difference operators. So you may already know that some sort of discrete version of the differentiation operator is what's called a difference operator. So these operators are defined as delta to the n. F of x is just simply n choose k minus 1 to the n minus k f of x plus k. So for n equals 1, the difference operator is just simply f of x plus 1 minus f of x. When n equals 2, the difference operator is f of x plus 2 minus 2 f of x plus 1 plus f of x, and so on and so forth. And you should think of these as some sort of discrete versions of differentiation. And these discrete versions of differentiation appear in the context of Mahler's proofs. Now, the other important thing to understand is that delta to the n is a linear operator. And so it's not difficult. I'm not going to prove this, but it's not difficult to see that the nth derivative or nth difference of f of x can be written as m choose j, delta n plus j f of x minus m. And this is to be thought of as some sort of Leibniz rule. So if it suffices to show the case when n equals 0, because delta n is a linear operator. If I show it for f of x, then I just apply delta to the n to the whole thing, and then you can get that result. So this is all you have to show. And you can do that very easily by checking what is that summation m choose j delta j f of x minus m. And when you write it out in longhand, and do the obvious interchange and summation, lo and behold, the inside sum turns out to be that binomial orthogonality relation that I talked about in the earlier slide. And the inner sum is 0 unless k equals m, in which case it's minus 1 to the m. And lo and behold, you get your result. Okay, so that's the proof of that fact. Now we look at any sequence that you give me, f of 0, f of 1, f of 2, dot, dot, dot. We'll define a sub n of f in this fashion. We know this is the right way to do it because by the inversion formula, we get a formula of f of k as a kind of like a Mahler series. But I want to establish another relation of a sub n plus j, some sort of shift. And this result is needed because I have to establish some sort of continuity property. And so I'm just going to establish this, state this result that I will just need. This is similar to the proof that I just gave here. So I'm going to leave that as an exercise for the students to do. So once we have this technical fact in place, we're now ready to prove Mahler's theorem. So here's Kurt Mahler, a contemporary 20th century mathematician. So his theorem is that if you have a continuous p-adic continuous function, f, and you define a sub n of f's in this funny way with the binomial coefficients, then a sub n of f actually tends to 0 p-adically as n goes to infinity, and therefore the series summation x choose k a k of f actually converges, and therefore it converges uniformly, and it actually converges to f of x. So this is Mahler's theorem. As you can see, it was proved in 1961. So it's a 20th century theorem for sure. So this should be thought of as the p-adic analog of the classical theorem of Weierstrass, that any continuous function on -1 to 1 can be uniformly approximated by polynomials. So I am trying to impress upon, especially the youngsters who are listening to these lectures, that there's a whole, p-adic world out there. And if you take your favorite theorems of calculus, you can just ask yourself the question, what is the p-adic analog of that? And many questions are still unanswered, as you can see from this context of the discussion that I'm mentioning. And it's not a small matter, actually. It's a nice melange of ideas, if elementary number theory and classical analysis that's involved in the proofs of many of these theorems. So the proof is a bit long, but uses the simple ideas that we've developed so far. So the proof of Mahler's theorem. So since ZP is compact and F is continuous, it is uniformly continuous. So given any positive integer S, there exists a positive integer T such that X minus Y being close implies F of X minus F of Y being close. And what does this say? It says that if X and Y are different by power of P, then we can translate this condition to say that F of K plus P to the T minus F of K is less than or equal to P to the minus S. So since F is continuous on ZP and ZP is compact, it is bounded there. And without laws of generality, say that the bound is 1, because we always normalize things, then it turns out that A sub n of P is also bounded by 1 for all n. And how do you get that? Well, you get that by using the fact that A sub n of F is given by this particular formula, and you apply the p-adic norm. And remember, the p-adic norm is less than or equal to the maximum of all the p-adic things. And since each of these is bounded by 1, everything else is also bounded by 1. So that's how you get that. And then that shift operator that I mentioned in the previous slide allows us to say that summation m choose j A sub n plus j of F is actually this alternating sum n choose k F of k plus m. We had this lemma earlier. I left that as an excellent. Now I need to use that. So the formula for A sub n given there, we have that A sub n plus t, p to the t, is this sum. This can be rewritten in this fashion. A sub n plus p to the t. I separate out the j equals 0 term and j equals p to the t term. So let me just go back here. So in here, I separate out the 0 term and n equals p to the t term from this particular formula, and we get this identity. And then notice now what we would like to do. We would like to exploit our congruence that we have for this f of k plus its p divides each of these binomial coefficients. Remember, I told you that p to the t choose j is divisible by p. So p divides all of these things. We find that the first sum, the p-adic value of this is less than or equal to the max of the p-adic values of the two things. Well, the p-adic values of each of these is bounded by 1. The p-adic value of this it's divisible at least by p. So the p-adic valuation of this is at most 1 over p. So I get this 1 over p a sub n plus j of p, which is bounded by 1. And for these, we know by our condition that f of k plus this particular thing, the difference here is divisible by p to the s, and therefore we can bound the whole thing by a 1. So replacing n by n plus p to the t in the penultimate inequality, the penultimate inequality being here, we get that a sub n of f of p is bounded by p to the minus 2 for n bigger than 2p to the t. And continuing in this fashion, iterating it, we end up getting that a sub n of fp is bounded by p to the minus s for n bigger than sp to the t. And therefore, a sub n of p goes to 0 as n goes to infinity. And therefore, this series actually does converge and converges to f of x, as both are continuous and equal on a dense set. And as the p-adic valuation of the binomial coefficient x choose k is bounded by 1, we end up getting the result. So that's basically the proof of Mahler's theorem. Okay, so some corollaries from Mahler's theorem. One is, if you give me any sequence in C sub p, remember what C sub p was. C sub p is the analog of the p-adic, was word analog of the complex numbers, the p-adic complex numbers. How did we get that? You take QP and you embed it into its algebraic closure. You extend the metric, the p-adic metric, to the algebraic closure, and then you take a completion again, and finally you get CP, and that turns out to be algebraically closed. So that's the definition of C sub P. You now can take any sequence in C sub P, and you can now define B sub n with in this funny way with this binomial coefficients. Then it turns out there exists a continuous function f interpolating those values if and only if this sequence goes to 0. And it's possible to fine-tune Mahler's theorem to get bounds on the radius of convergence if we have a p-adic estimation of the coefficients. And so the power series gives you an interpolation, but where does this thing converge? Well, it turns out it converges in a certain region, capital R. And what is this capital R? Suppose we have this number, this R sub P, we met this number before with the exponential function. And suppose that we had an estimate, a p-adic estimate for each of the coefficients, then f of x can actually be expressed as a power series with the radius of convergence at least given by this quantity. So this is slightly larger than the region that we started out with. So we can refine some of our work earlier. So now that I've given you an outline of Mahler's proof, we can make some refinements. If I have a function, continuous function on ZP, which is CP valued, and the Mahler series is given by this f of x equals x choose k, C sub k, then f is the restriction of an analytic power series if and only if ck over k factorial goes to 0 as k goes to infinity. So that's the refinement that I was talking about. And a simple application of this particular theorem to the function n to the s, which you considered earlier, with n congruent to 1, tells us that n to the s can be written as 1 plus n minus 1 to the power s. And then using the binomial coefficient, you see that it's equal to k equals 0 to infinity, s choose k, n minus 1 to the power k. Now, since n is congruent to 1 mod p, n minus 1 is divisible by p, and n minus 1 to the power k is divisible by p to the k. Therefore, this coefficient actually is going to 0 in the p-adic metric. Now let's come back to the question of the p-adic gamma function. So in the earlier slides, I impressed upon you the fact that the p-adic, our guess as to what the p-adic gamma function should be satisfied that congruence condition 5.1. And now let's look at this function when p is odd first. P equals 2 is always a problem, and so it has to be considered separately. So we'll just consider p odd first. From the definition, we have that gamma p of n plus 1 is minus n gamma p of n if n and p are relatively prime, and minus gamma p of n if n and p are not relatively prime. Remember what gamma p was? Gamma p was the product of the j's less than gamma p of n was product of the j's less than n, which were co-prime to p, and then there was a minus 1 to the n as a sign of in front. And so if you just use that definition, you'll see that this is the recurrence relation that it satisfies. This should be thought of as the analog, the p-adic analog of gamma of s plus 1 being s times gamma of s. I think from the classical gamma function, gamma of s plus 1 is equal to s times gamma of s. And therefore, this is the analog of that fact. And now we can say that gamma p of x plus 1 is hp of x times gamma p of x, where hp now is minus x if xp equals 1 and minus 1 if xp is less than 1. And what do we want to do? We want to find a continuous function on ZP that interpolates these values. So by that theorem earlier, what do we have to show? We have to show that whenever k and k prime are closed p-adically, gamma p of k and gamma p k prime have to be closed also. That's basically what we have to show. So whenever I tell you in the p-adic metric, something being close to something else means that the difference is divisible by a high power of p. So it boils down, the so-called continuity condition in the p-adic context always boils down to checking congruences. So it goes back to elementary number theory. So if I look at keeping in mind that gamma p of x is always coprime to p, because we never multiply by anything which has p as a divisor. So gamma p of k is an invertible element in this, and so is gamma p of k prime. They're both invertible. So essentially, what does it say? This says that one has to be congruent to gamma p of k prime divided by gamma p of k. And when I write that definition down, it's minus 1 to the k prime minus k times the product of the j's between k and k prime, which are coprime to p. So that's basically what we have. And so the question is, we have to check this. We have to check whether or not this condition is satisfied. The product runs over every congruence class mod p to the n exactly once, and therefore the product is the same, this product between k and k prime being k plus k1 p to the n. So this particular product can be related back to this product over j less than p to the n coprime to p. Each j has to be coprime to p, and this is again a kind of a generalization of Wilson's theorem. See, what is actually Wilson's theorem? Wilson's theorem generalized says in any abelian group, the product of all the elements is actually congruent, equal to the product of the elements which are of product of the elements x, such that x squared is 1. So we have to just check what are the elements which are congruent to 1, which are squares mod p. This is the product of all the coprime residue classes mod p to the n, and as we can pair up j with j inverse, the only elements that survive the product are elements that are of order 2. And these are plus 1 and minus 1 as discussed earlier. Remember, in the case of p odd, we knew x squared equals 1 mod p has only plus or minus 1 as a solution, and by Hensel's lemma, you can lift that to plus or minus 1 in QP, and therefore the product is simply minus 1. So that's basically where we are with this. And when p equals 2, the p-adic gamma function can be defined in the same way as before, setting the product of the j's less than n, with j being odd. And using that, if we want to interpolate the p-adic gamma function, we have to look at the sequence at n plus 2 to the s and at n, and then compare them. And then when we do that, the product on the far side there, the product above is a product over a complete set of coprime residue classes mod 2 to the s, and it again reduces to the product of elements of order 2. And you will recall when we discussed Hensel's lemma in the context mod 2, the solutions of x squared equals 1 mod 2 to the s are 4 in number, 1 and minus 1 and 2 to the s minus 1 plus 1 and 2 to the s minus 1 minus 1. And therefore, when you look at those and you work it out, it turns out this congruence holds. Now, in classical complex analysis, you will recall that the gamma function satisfies a functional equation. Gamma of x and gamma of 1 minus x is pi over sine pi x. And the question then, again, one can ask, is there a p-adic analog of this result? And the answer is there is. The theorem is, if p is an odd prime, gamma p of x and gamma p of 1 minus x is minus 1 to the L of x, where L of x is defined as the element of 1 to a p, satisfying the congruence L of x is congruent to x mod p. Remember, x is a p-adic number, and p-adic numbers have expansions, a0 plus a1p plus dot, dot, dot. So x would be a0. So how do you prove this? Well, we go back to the definition. 1 is gamma p of 0, and gamma p of minus 1 times hp of minus 1 use that functional equation, you can't use that recurrence relation, gamma p of 2, h of p minus 2, h of p minus 1, and so on and so forth. And so recursively, we find it's that this 1 is equal to gamma p of minus n times hp of minus j going from 1 to n. And looking at the definition of what hp of j is, well, it's equal to minus 1 p divides j and j otherwise. And therefore, when you work that out, gamma p of minus n and gamma p of n plus 1 turns out to be minus 1 to the greatest integer of n over p plus n plus 1, which equals 1. So this is the analog of that theorem. And then when you work it out, so we've proved this particular thing, and changing n minus 1 instead of n gives me gamma p of n times gamma p of 1 minus n equals minus 1 to the power n plus n minus 1 over p, greatest integer. So we want to analyze what is the meaning of this exponent. Write n in the p-adic form, a0 plus a1p plus dot dot dot, and when we look at n minus 1, subtract 1 from this, you get a0 minus 1 plus dot dot dot, divide by p, and then you get yes, is there a question?
ये रिएक्शन अनबैलेंस्ड है, इसको हम लोग को बैलेंस करना है, ठीक है?
I'm sorry, I will just check
I
out.
request all participants, you please ask your questions after
Yeah, okay. Anyway, so we have, we take the p-adic expansion of n as a0 plus a1p plus a2p squared and so on and so forth, and subtract 1 and divide by p, and notice that you get this particular expansion. Let's first consider the case a0 is not 0. Then this divided by p is a number less than p. When you take the greatest integer, this disappears. So the greatest integer of n minus 1 over p equals a1 plus a2p plus dot dot dot. And so the calculation of that particular exponent then turns out to be exactly L of n has been defined, which is the number n minus p greater than n minus 1 over p turns out to be exactly And in that case, what happens is you get n minus 1 equals p minus 1 plus b1p and so on and so forth. When you take the greatest integer of that, you end up getting b1 plus b2p and so on and so forth. And that gives you that, again, in this case as well, it does work out to be L of n. So the result then follows by continuity. So this proves that we have this functional equation also in this kind of p-adic context. So you can now have some fun with asking many questions that go to a handbook of calculus or something, look up what the gamma function is doing, and then ask the question, what's the p-adic analog of that? So many of us learn in a basic calculus course that gamma of a half is square root pi. And the question is, what is the p-adic analog of this? And as key, you've got to understand that every time we ask this question, it really has to do with number theory. That's the point. I mean, something very precise about numbers shows up. So what's the p-adic analog of that? Well, in the previous example, I just said gamma p of x times gamma p of 1 minus x is minus 1 to the L of x. So you have to calculate what L of a half is. And we find that, what is L of a half? Well, L of a half is defined as that you have to look at the p-adic expansion of 1/2. Well, how do you get the p-adic expansion of 1/2? Well, L of a half is the same as L of p plus 1 over 2. And L of p plus 1 over 2 is exactly p plus 1 over 2 if p is an odd prime. So we get that gamma of p of half squared is 1 if p is congruent to 3 mod 4, and minus 1 if p is congruent to 1 mod 4. Okay, this is interesting. So gamma p of a half squared is 1 or minus 1. And so the question is, what is then gamma p of a half itself? What is gamma p of a half? Well, gamma p of a half squared is where gamma of a half is square root pi is a transitional number. We see that gamma p of a half has to be an algebraic number here. If p is 3 mod 4, I'm not going to do this. I just want to say half is a little tricky and involves number theory. So let me discuss the case when p is congruent to 3 mod 4. It turns out that gamma p of a half, when prime is congruent to 3 mod 4, we're in the case that the square is equal to 1. And we already agreed that the numbers x such that x squared equals 1 are only plus or minus 1 in the p-adic case. So which one is it? When is it plus 1? When is it minus 1? And the sign depends on the parity of the class number of the imaginary quadratic field. I haven't discussed class numbers at all in this series of lectures, but some of you may know about it already. The class number is an invariant attached to any number field, which kind of measures the deviation from the unique factorization property. So if the class number is 1, that means the ring of integers of the number field is a unique factorization domain. And if the class number is bigger than 1, it means it's not a unique factorization domain. And larger this class number is, the farther it gets from being a unique factorization domain. So that's the intuitive understanding of what a class number is. And if we take what are called quadratic residues, that is squares mod p are called quadratic residues, R1, R2, etc., which are less than p over 2, and R1 prime and R2 prime, which are also quadratic residues greater than p over 2, and N1, N2, and so on and so forth. Somebody has a question. Umesh Shankar has a question.
So when you mean that the larger the class number, the further away from U of these it is, like, how do you exactly characterize this notion of further away from U of these?
Oh, just the size. So if I have a class certainly not a unique factorization domain, and so somehow the class number measures the deviation from unique factorization. Actually, the class number is the size of a particular group, and the structure of the group gives me some knowledge about the factorization of the numbers. Okay, so this is a chapter in algebraic number theory, which requires more exposition. We will suffice it now just to say that the class number measures the deviation from unique factorization. Okay. All right. Now, if we take R1, R2, and so on and so forth to be the quadratic residues less than p over 2, and R1 prime, R2 prime to be the quadratic residues greater than p over 2. You see, from 1 to p, they're squares mod p. Some of them are sitting in the interval 1 to p over 2, and some others are sitting in the larger interval from p over 2 to p. And we'll write it this way. And N1, N2, the N residues less than p over 2, then it turns out that p minus 1 over 2 factorial, you'll remember p minus 1 factorial is by Wilson's theorem minus 1 mod p. But if I only took half of them, all of a sudden some interesting things emerge. P minus 1 over 2 factorial turns out to be the product of R1, R2, dot, 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 N1, N2, and so on and so forth. When we look at the product of all these things, this is done by getting those which are residues less than p over 2, and those which are non-residues less than p over 2. We multiply them together, and then we find that the non-residues can be thought of as p minus R1 prime, p minus R2 prime, which are the residues bigger than R over 2. And so when we combine them all, you find that it's equal to minus 1 to the n times R1, R2, dot, dot, dot. And then the product of all the squares again is 1. Therefore, p minus 1 over 2 factorial is congruent to minus 1 to the power n, where n is the number of non-residues which are less than p over 2. So this is the subtle idea. And now the sum of the residues plus some of the non-residues is, of course, the full the sum of the residues less than p over 2 and some of the residues non-residues less than p over 2 is the total number p minus 1 over 2. And if h minus p is a class number, then now it goes back to Umesh's question. Exactly how do we determine this class number? Well, that's a deep theorem of Dirichlet. Dirichlet proved that the class number of q root minus p can be given by the difference between the number of residues less than p over 2 minus the number of non-residues less than p over 2. And by the way, notice that this number, since it's positive, it tells you there are more residues less than p over 2 than there are non-residues less than p over 2. A fact that I don't know, and I don't think anybody knows, of how to prove without using this class number formula. Anyway, this is what we end up getting, and so it's now an easy exercise to show that gamma p of a half times p minus 1 over 2 factorial is actually minus 1 mod p. And so the sign of gamma p of a half is determined by the parity of the class number of h of minus p. So whether when h of minus p is even or odd is determined by enters into the evaluation of gamma p of a half. Now, Gross and Koblitz in the 1970s.
Sir, just one question here. The 2 minus 2 by p, that is the Legendre symbol?
Yes, thank you. Yeah, thank you. Yeah, thank you for telling me that. That's the Legendre symbol, exactly. 2 over p is plus 1 when 2 is a square mod p, and minus 1 when 2 is not a square mod p. And so this is always plus or minus 1. So this will either be 2 minus 1, which is 1, or it'll be 2 plus 1, which will be 3. And it's an interesting fact that then 3 will have to divide that thing. Yeah, thank you for putting that in. Now, so this whole business of the p-adic gamma function is a 1960s, 1970s discovery. Certainly was happening when I was a graduate student, and Gross and Koblitz at the time were working on this p-adic gamma function. And it's connected with many classical questions, Gauss and Jacobi sums. They can be all thought in terms of the p-adic gamma function. And so this enabled them to derive a classical theorem of Stickelberger, giving the ideal factorization of Gauss sums in a more precise form using the p-adic gamma function. And in that context, they were able to show that gamma p of a over n is algebraic whenever n divides p minus 1. But the proof of this fact uses p-adic cohomology, and it would be very nice to find a more elementary proof. And it'll also be nice to resolve the algebraicity of gamma p of a over n in general. So I told you that before these numbers, we had that functional equation, gamma p of x times gamma p of 1 minus x is equal to minus 1 to the L of x. We had that, and it tells you that gamma p of x and gamma p of 1 minus x both, they could be transcendental, but the product turns out to be an algebraic number. Therefore, the question of whether or not each individual one is transcendental is still open in general, even in the p-adic context. Of course, it's open in the classical gamma function context as well. So more or less, this is all I wanted to say. What I want to set up for next time is to discuss the Kummer congruences again, and put that in the context of p-adic interpolation. And the p-adic interpolation, this as discussed in today's lecture, was trying to find a function, an p-adic continuous function that interpolates those values. So today we discussed somehow how do you interpolate factorials in the p-adic context. And next lecture we will talk about, which will be the last lecture, we'll talk about interpolating the Bernoulli numbers, so the bk over k. Can I interpolate those? Is there a p-adic continuous function such that at k, it turns out to be important aspect of research. On one hand, you may be looking at something very classical and it may be viewed as simply a congruence, but by taking another perspective, you get more insight and a new kind of world opens up. So that's basically what I want to do next time. So thank you very much for your attention. Time for chai. So there we go. Chai GPT, genuinely pure tea. That's what GPT stands for. AI stands for adrak and ilaichi. So this is apparently a tea stall in Andhra Pradesh because that's Telugu down at the bottom of the screen. Okay, so thank you very much. Time for chai.
So thank you very much, sir. So I request the participants to go ahead with your questions.
Yeah, so this gamma p a by n, is it expected to be transcendental otherwise? That is, n does not divide p minus 1. Are there any guesses?
I don't think so. I think, yeah, I don't know. I don't know the answer to that question. That's a good question. All the cases that we know, they're algebraic.
Oh, I see.
And I'm guessing it's algebraic.
Uh-huh. But
Yeah.
are there any methods, like there are
Yeah.
some methods which show
Yeah.
that number in usual cases transcendental. Some methods have been devised. So are there
Yeah.
some methods in the p-adic situation to decide
Yeah.
totality?
Yeah, no, the transcendental number theory over the p-adics is another, chapter altogether. Actually, there are many things. There's, for example, a p-adic version of Baker's theory, linear forms and logarithms, and that was, I believe, proved by Brumer. Brumer, I think, is the one that. So it's a different mindset to wrap. Proofs don't go mutatis mutandis into the other context. They have to be modified. So it's a different world. You just have to wrap your head around it. But I'm hoping to entice some of the younger students in the room to pursue this study, because there are lots of open questions, as you just asked, about the nature of these values. And you can look at the beta function. What is the p-adic analog of the beta function? What is the p-adic analog of hypergeometric series? And so you know that there are many questions of transcendence in the hypergeometric context, so you can ask the same questions here. And then it's not so hard as you think it would be, but it hasn't been researched.
Okay, yeah.
So any questions?
Sir, the way you bifurcated those R and R dash, isn't it
Yeah.
like one of the proofs of Gauss quadratic reciprocity just 2 slides earlier?
Yeah.
That idea was seen there.
Yeah, you're right. So let me just share my screen here and go back. You're right, absolutely. Oops. I think I'm back to the first. So let's see. You mean this one?
Just the previous one, just before this. The where you introduced R dash, yeah, this one.
This one, okay,
Where
yeah.
you introduced R.
Yeah, it's similar. It's similar. They're not quite identical, but it's similar. You're absolutely right. The nature of the sign of the Gauss sum calculation is entering in this as well. You're absolutely right. And Gauss had a lot of trouble trying to find out what the sign of the Gauss sum is, and it had to do with questions of residues and non-residues and how they're distributed. You're absolutely right. Yeah.
Okay, thank you. And also on the first day you had said that zeta 3 is irrational. So
Yes.
what are the kinds of techniques or methods used for that?
Yeah,
Could
it's a
you
good
just
question.
some
Yeah.
scale?
Yeah, it's a good question. The question are basically Apari, who started this, found a new continued fraction expansion for zeta 3. And using the partial quotients of that continued fraction, actually, he said he was inspired by works of Ramanujan in discovering this. And so he found some new rational approximations of zeta 3 which ended up showing that it can't be a rational number because it was too good as a rational approximations were too good. And he got this sequence kind of inspired by work of Ramanujan. And to imitate his method in the case of zeta 5 and zeta 7 has been unsuccessful. However, all of the new ideas that seem to be used deal with some form of hypergeometric functions and the study of rational function approximations to hypergeometric functions. So probably something similar can be done in the p-adic context. I'm not sure.
Thank you.
Yeah, you're welcome.
Madam, you please conclude.
So if there are no further questions, let us thank Ramamurthy sir for his nice lecture. And I hope we all have AI inspired tea now and come inspired for tomorrow's lecture also. Thank you very much, sir. So tomorrow, please accommodate us if there is an interruption from the administrative side.
Okay.
So if there is some delay, we request you to, we will start with the lecture probably, and then if sir joins late, then we may have some tweaking.
Okay.
So thank you very much.
You're welcome. You're welcome. Have a good day. Bye. Yeah. Bye.
So on behalf of the Department of Mathematics, also thanks the Ramamurthy sir, also thanks to the Professor Devre sir and all the participants. Okay. Good day to all.
Okay. Thank you. See you tomorrow.